Thank you guys so much for coming. My name is Tom Langford. I'm a staff member here at the Center for Research Computing. I am part of the research support team. If you've sent in emails to ask for help on any of our clusters, odds are I've responded to at least some of them. Today we're going to talk about a topic that I've spent a lot of my mental effort on, which is how to tune and get the most performance out of Python code. Python's a language that I really love working in, and one that I think is really well suited to lots of different problems that we come across in research. And so finding the best way to get the most oomph out of your code while keeping an eye towards actually, the goal is to do science or to do whatever you're after, not necessarily just to write the code for itself. So I started with an outline that had two parts, and then I was like, oh, actually, I kind of want a third part. Actually, I kind of want a fourth. And so we eventually got to having 5-ish parts, but I promise they're not so bad. So we're going to talk a little bit about Python packaging, how and best practices of managing that. Then we're going to ask the question, why is our code slow? And actually find ways to identify bottlenecks and things that are slowing it down. We're going to talk about resource management and monitoring of resources, especially as it relates to running code on clusters and on our clusters in particular. And then after part 2, we'll probably take a little bit of a break. We'll stretch our legs. And then we'll do part 3 and 4, which is parallelism, splitting up jobs to run things at the same time, or splitting up jobs to run asynchronously. Both locally on your personal machines or also on the clusters. And then part 4 is a selection of 3 different packages that accelerate Python in different ways. So either with compiling or with distribution running on multiple compute nodes, or with running on GPUs. So we'll dive into that at the very end. So Python packages. There are a number of ways to install and manage Python code and packages. The 3 biggest ones that are present on our clusters are using Conda, using virtual environments with pip, or using software modules, so things that we install and provide as a module for researchers. For this talk, we're going to focus on Conda because it's the most transferable. It's the easiest to kind of take from one machine to another and to set up. It's simple to install. It does not require administrative privileges. We install Conda on the clusters for everyone to use. And we use an installation that's actually provided by Conda Forge, which is the open source version of Conda. And I strongly encourage all of you to use Conda Forge provided tools rather than the ones provided by Anaconda. There's some terms of services that come out of the Anaconda organization that seem a little bit counterproductive to research, whereas Conda Forge is pure open source software. The key thing, it started as mostly a tool for compartmentalizing environments and actually being able to say, this project, I need these tools. This project, I need a slightly different subset of tools. This project, I need ones that are conflicting with the other 2. And it allows you to put them in little buckets and keep them separate so that if I'm developing code with 2 different groups of people, I don't accidentally break each project every time I upgrade a package. So we're going to use Conda for this tutorial. And in fact, all of the packages that you need for this tutorial are here. I'm not expecting you all to type it. This is not really an interactive, though all of the code that I have is provided, and so that and these slides will be provided too in this GitHub repository. So it's github.com/ycrc high performance Python with underscores. This QR code should take you right there. Once the talk is finished, I'll upload the slides to it after this session, so that the slides will also be a reference there. But this contains all of the code samples that we're going to use today, and some notebooks that we're going to use as well. So I'll give a second if people want to grab that, but if not, no worries. Okay, so the first question that you should always ask when working with a code base is, if you're unsatisfied with the performance, you have to ask the question of why. And there are a lot of different answers that could come from that, but the question of why is my code slow is really important. And I I love XKCD. I read it almost every day. And so, this is a flow chart that Randall Munroe come up with. Are you prematurely optimizing or just taking an opportunity to do it right? And then it says, well, come on, you're prematurely optimizing. So if you're not looking at where your code is slow, then you're jumping the gun. And in fact, I sat down to write a better one that might actually be useful. And so we'll just kind of talk through it. I think anytime that I'm approaching a new problem, I work in pseudocode first. I just write down, what do I actually want this code to do? And I write it down in just words. And then I do something that's quick and dirty and fast, and it takes me 10 minutes to write. And I don't worry about performance. I just write something quick and dirty. And then I ask, is this fast enough? Where that is a very squishy question. It's fast enough for me, for right now, for this circumstance. And so, if yes, check, does it work at the scale I need it to work at? Okay, I tested it works for, n of 100, or maybe it works for 5 files or 5 random number seeds, but does it work at the scale I need it to work at? And if yes, you're done. Just walk away, right? You got it done, you automated some boring stuff, and you declare victory. But if not, you go into this loop of profiling. So the first step is to actually profile the code. Look at where is the code spending all of its time, and then identify if there are bottlenecks. Is there anything that's obvious, like, oh, it's spending 99% of the time in this line. Well, that's the line I should care about. And now I have an informed decision about what to do about it. So you can either fix low-hanging fruit with simple things, or you could start adding complexity, leveraging new packages, different tools, use a GPU, different things that try to enhance your performance. But this is kind of at the end when you fixed all of the low-hanging fruit and you still have performance that you need to get out of it. So to me, the question is not so much why is important, but where. Where is my code slow? That is the one that then becomes actionable. And so I always say, before you start optimizing, you have to identify the problem. And then you only improve the sections that are actually contributing to the runtime in a significant way. I might have a function that takes a long time and is really slow, but if I only have to do it once, it may not contribute meaningfully to the total runtime, versus a slightly inefficient for loop that I could optimize, because it has to do a million iterations of that loop, and even a small percentage improvement improves the throughput of the whole system. So Python has a lot of different profilers that people have produced. The C profiler is built in. There's one called kernprof that's also called line_profiler. The one we're going to talk about here is called Scalene. It's new. It's within the last couple of years. This is its GitHub. The key for this is that you can actually profile not just CPU, but you can also profile memory use, and you can profile GPU utilization. And so it's the only profile that I have found that can achieve all 3 of those while also being fast and efficient and not contributing its own overhead. You can install it via Conda, and it can also be sprinkled into Jupyter Notebooks if you're working with some prototyping code and you want to see, what in this cell or this piece, what's slowing me down. It'll generate either a web interface that you can click and hover and sort things, or you can also have it just spit out a line-by-line CLI interface that you can run in a terminal. I have not played with it, but I've been told that if you have an OpenAI key, you can punch it in and it will let ChatGPT do its magic to tell you new ways to make your code not run super fast. But that's a different topic. So an example. A very standard thing to do in Python is to work with lists or arrays of objects. And so here on the left, I have a list where I have a function, and I'm going to take some number of elements in that function. So it's either going to be an integer here that's like 1 to 1,000,000. I'm going to create 2 empty lists, and then I'm going to loop through the length of this, and I'm just going to append the values. So I'm just building up a list that's 1, 2, 3, 4, up to the number n. And then I do a separate loop where I take the values in list 1, I square them, and then I append it into list 2, and I return list 2. This is incredibly inefficient and dumb code, but it's an example of something that we'll see why in a second. Alternatively, you could do this with a NumPy array. So when we asked for people to sign up, generally people were familiar with NumPy. Is that true? Okay, wonderful, because I'm doing a whole lot of assumed knowledge about NumPy, so hope that's not a problem. So here we're doing this with NumPy. We have the same number n. We generate an array that's just a range starting at 0 going to n, and we just return the square of that using a built-in NumPy function. And so we're going to compare the two codes. This is the report that scaling prints out when you run it for, in this case, it's 10 million elements in the list approach. And so there's a lot going on here, but you can see this is the line by line of the code. At the top, it shows actually a memory usage footprint. And you can see in the middle of it, it peaks to have the max memory, which is 700 megabytes. And then it spent 2.5 seconds running this code. And you can automatically see there are two lines that are spending most of the time. So the time here is 26% and 33% of the Python code. It also has a small amount of code that's native and in the system. This has to do with the way that the code is actually allocating memory. So these things all sum up together to be 100. But the memory, you can see this is big spikes in memory allocation. And in this particular, it grows up to be half the total memory usage of the system. So this is not an efficient way to do this. And this tells me this line and this line, these appends, are the problem. These are the things that I want to avoid. And so if I profile the NumPy solution, we see a number of things that are key. One, the memory usage is way lower. And that's because NumPy arrays are more efficient containers of data than a list is. A list can have any object in it. So even though I'm just appending an integer to it, a list can have a function in it. It can have strings in it. It can have anything in it. So it has to be much more verbose in the way it's storing those objects in memory. Whereas NumPy assumes a data type. I didn't tell it a data type, so it's assuming a rather generous one, but it assumes a data type. So the memory is about, I don't know, maybe a fifth of what it was before. And instead of doing 2.5 seconds, it did it in 400 milliseconds. So we improved the code speed considerably by doing it with built-in functions and specifically using array operations in NumPy. Right. So general best practices in Python, there's, if you ask the internet, there's a million different think pieces on Medium or, towards data science or whatever about what are best practices. And I think they're all very specific to the different domains. But in general, there's a lot of built-in functionality in packages like NumPy and SciPy that are Python at the surface, but are C and Fortran code underneath. Those tools are incredibly well optimized, and it's best if you leverage those in whatever way you can. They're not a panacea. There are problems that it can't solve, and we'll talk about some of that later. But in general, use a NumPy array if you're storing data instead of a list. Use data types intelligently to work with the data that you know are going into it. And use vectorized operations when you can. This particular one took the whole array and raised every element to the second power in one step. And it used C code and Fortran code underneath to do that, rather than using Python at the surface. So don't reinvent the wheel, use built-in functions. File input and output is another really common problem. Who works with kind of data files or binary files or images or things like that with Python? So, and if you're doing that on the cluster, all of our clusters have what are called networked file systems. So every compute node in the cluster can see the data that's on, if you're on Grace, it's the Gibbs file system or Palmer file system. If you're on Milgram, it's called Milgram, confusingly. But McCleary is also Gibbs and Palmer. And so all of those data are available everywhere, which is incredibly convenient, but also means that accessing it, it's not just you accessing a local hard drive. It's you asking a separate set of compute nodes to give you that data over a network. And you're not the only person doing that. There are other people on that system. There are other people doing other data-intensive tasks. And so if you're asking, to your file system, please give me 4 bytes of this big giant file, and then give me another 4 bytes, and then another 4 bytes. Every time it does that, it has to wait its turn to get its chance to get data out of the system. And it can be very, very inefficient, and it can be a bottleneck. And so when working with data files, if you're seeing I/O being the limiter, think about staging data to the local hard drives. So every single compute node in our cluster has a local hard drive that's flash storage that you can use to stage data in. So you might copy a whole data file locally, and then you can churn on it a lot. Or you might bring a bunch of data over so that you can act on that without running into network congestion. There's also chunked I/O operations where instead of asking for 4 bytes, you could ask for the entire file, or you could ask for a big chunk of it. That minimizes overhead as well. And finally, there are a lot of Python optimized file systems, or file formats, excuse me, that are designed for performant operations. And Pandas and Numpy have lots of functionality that's good at reading binary data or tabular data out of CSV files or things like this. But there's a growing number of tools, and Pandas in the next version will do this by default, that use an arrow tool from Apache as their default data format. And Feather and Parquet are optimized file formats that are designed for high-speed read and high-speed writing. So these are things to start looking into if you find your code being constrained by I/O. So we're gonna talk a little bit deeper about resource management and monitoring the resources that you're using on the cluster. So a lot of this will be applicable if you're working on your local machine, but not all of it. Some of these are cluster tooling. But in general, clusters are not like workstations. They're not like your laptop. You have to request specific resources. And you have to think about what is the right amount of, how many CPUs should I allocate? How much memory should I allocate? It changes my wait time for the job to start, but it can also change the performance of my job throughout. And sometimes it can prevent other jobs that I also want to run from starting. So you need to tune and optimize your resource request to make sure that you're getting the most science done. So we're going to talk a little bit about some key problems that come up with resource requests on the cluster, and I have a lot of examples of this. But in general, you want to be careful about oversubscription whenever you work with parallel libraries like multiprocessing, joblib. We're going to talk about more of that in a little bit. We want whatever CPUs you request, we want them to have exactly one thing happening on those CPUs at a time, and for that to be running at 100% CPU. So we want it to be not context switching between different processes. We want every CPU to be running at 100% and not waiting on data or not waiting on network access. And so those are things that we want to look at and monitor during jobs that run on the system. And so we also want to look for, is there memory growth? Is there a problem with the way that I've coded it and I have a memory leak? That could lead to inefficiencies. And finally, we should really think about the whole computing job that you're working on, not just a specific task of it. And we'll talk about what that means. So the 2 tools on the cluster that I recommend for using to watch in real time your resources are HTOP and NVIDIA SMI for GPU-like jobs. So everyone should be aware, when you run a compute job on the cluster, you have access to that compute node, even if it's a batch job. So if I run a batch job and it's running for a day, I can log into that compute node to watch how the process is running. So in particular, you can get the list of where your compute jobs are running by running an SQ command. So this tells you the names of these compute nodes where your jobs are running. And then you can just SSH into those nodes. So you can log into them and you can watch the processes, either with HTOP, which is kind of like Activity Monitor on your Mac or Task Manager on your Windows PC, or you could use NVIDIA SMI, which is a command line tool to show what's happening on the GPUs right now. And doing this process is incredibly important for new workflows, things that you're just starting at. You want to make sure that it's working the way you think it should be working. And the only way I know to do that is to actually log in and watch it. So what does this, okay, we're a little out of order, but that's okay. There's a very new tool that we've developed we've deployed on all of our clusters is a tool called job stats. Given a job ID number, on any of the clusters, you can run job stats job ID number, and it will print out a report that shows the utilization, the average utilization over time of the different resources. So this includes CPU, memory, GPU utilization, and also GPU memory. And in this case, the GPU memory is the high watermark. The GPU, so both of the memories are the high watermark, whatever's the most memory that I've used, whereas the CPU and the GPU utilization are the average. So this particular job that I ran only used about half of the allocated CPU time, and it used about 15% of the GPU time. That, to me, is not a very efficient job. It's not making good use of the resources. It used all of the memory, so that's good, but it's not using these resources efficiently. So that's a key to me, that I need to go and look at this job and understand what's actually happening, why is it not performing as well. But these are averages or points in time, and I don't get a ton of information out of the command line report about when that's happening or why. And so there's a web-based version of this that actually you can access through the on-demand web portal. Every single job has a web page that you can load that shows the CPU utilization, memory utilization over time. So this is the CPU usage over time. And you can see this particular job has big stretches where it uses 100%, all of the CPUs that have been allocated, but it has big stretches where it uses maybe only 10% or 15%. So this job, something in the code is not using all of the resources all of the time. And that might be an indication for me to, maybe there's a problem with the code here, or maybe it's a bottleneck. It's waiting on something else, some disk I/O, or it's waiting on something. Or maybe there's just a function here that can't be efficiently parallelized across all of the CPU cores I've given it, and that's a space and time I want to go look at. So this web-based tool, I should have put the URL, but if you go into on-demand and open up what's called the user portal, in the user portal there's a table of recent jobs, and you can punch in a job ID number, and you can actually get this report for all of your jobs. This is very new and occasionally stops working, and we're trying to figure out why it's doing that, but let us know if it does so. One thing that's kind of handy as well, this code can also show GPU usage over time. And you can actually see in this particular example, the time when this is not super CPU intensive is time when it is GPU intensive. And so it's an indication that there's an interplay between the CPU cores and the GPU cores that are preventing the CPUs from being utilized because it's waiting on something from the GPU. So something to consider. However, let's actually look at HTOP. So this is what happens when you log into a node where a job is running. You run the command HTOP. You get a thing that looks like this. So let's talk about what is happening here. This is a lot of information. At the top, each of these little sliders is one of the CPU cores that's on this compute node. If I've only been allocated one of these, it still shows all of them, which is a little unfortunate. But in this particular case, this job has the entire compute node. So 0 to 23, there are 24 cores on this node. All of them are running at 100%. And I look down here and I see for every CPU, there is exactly one task that's running on it, and they're all running at 100% usage. Close enough. This is a job that's nicely laid out. It's working the way we expect it to. I see the right number of tasks. There's no empty CPUs. There's no CPUs that are it's not like there are 10 tasks all fighting for access to one of these CPUs. This is working the way it should. This job is not. So this is a different job running on our cluster. And in particular, you can see these are the processes that are running. There are 8 of them. The top level is this one. But each of these is running at roughly 1/8 of 100%, so 12%. So here we have 8 processes that are all fighting for a single CPU, because this command was given with 8 threads, but they didn't request 8 CPUs. They only asked for 1. So this is an example of a job that if I only look at the average utilization, I used all of the resources available. I used 100% of that one CPU, but I didn't use them efficiently because each of these processes is fighting the others. And the CPU has to spend time switching from process 1 to 2 to 3 to 4. And so it's not an efficient use of this CPU. So by logging in and looking at these processes in the layout, we see this is not working right. And it could probably go more than 8 times faster. Because each time the CPU switches between threads, it loses efficiency. Okay. Similarly, NVIDIA SMI gives a report for the GPU usage. This is a job that was running on Grace this morning. And both of these GPUs are running at nearly 100%. This is a perfectly sensible, normal GPU-looking job. Life is great. This job, and I've obscured the top half of the report to protect the innocent. This job has 100% CPU utilization, but it has 4% GPU utilization, 5%. So something's not right here. If we think about this, there's been exactly one CPU allocated. There's one core. There's a ton of memory. The memory usage is okay. But the 3 GPUs are not being fed with enough data to be active. So this one CPU is just trying its absolute best to get data to these 3 GPUs, and they just sit there doing nothing. And we can see that if we log in and we look at the job, we can see there's one CPU that all of these processes are running on a single CPU, and it's trying its hardest to feed data to these GPUs, and it just can't keep them busy. And so these are 3 A100 GPUs for this particular job. This is an expensive job, when you think about how the cost of these resources, and it's being hamstrung because the resources don't line up. So you don't have enough CPUs to keep the GPUs busy. So pulling these two up in, whenever I'm working with GPU code, I pull up htop in a tab and I pull up the other right next to it. I meant to obscure that username. I'm going to keep going, because I didn't. So we've got we've talked about some best practices. We've talked about accessing and monitoring resource utilization. We want our jobs to go faster. A really obvious way is, well, I'll just run some stuff in parallel. So there are 2 flavors of parallelism that I want to harp on. There's explicit parallelism, where I'm saying, computer, you do this part here, you do this part here, you do this part here. I'm telling you exactly what to do. There's also implicit parallelism, where some library that I'm loading is saying, I think I can split some of that up. And I'm going to do some of it on my own. I'm not going to tell them that I'm doing it, because they want it to go faster, so I'll just do it. These are perfectly sensible things to do. It's hard to do them both at the same time. And in particular, if you try to mix these, so Numpy does a lot of that implicit parallelism. So it can use its own parallel libraries under the hood with either OpenMP or MKL to get parts of you take a big long list or array of numbers, it can do actions on sections of those in parallel. But if I'm also trying to do something explicitly with multiprocessing or with joblib or other things that we'll talk about in a second, this can collide in a way that you get that oversubscription. You get multiple things trying to access and vie for the same resources, and that can slow everything down. So it doesn't just do no harm, but it even makes things slower than running them serially. So we have to be careful. So you can control the implicit parallelism in Numpy, but also in other libraries with these 2 environment variables. And so I would just say, if you want to do explicit parallelism, if you want to use multiprocessing or joblib or Dask or things like that, you want to set these to be 1. You want to disable the implicit parallelism, because you have other plans for those CPUs. You don't want Numpy getting greedy and think that it can use threads when you actually have those CPUs allocated for specific reasons. So if you wish to do explicit parallelism, set this equal to 1. Okay, so we're going to talk about explicit parallelism, and we're going to focus at the moment on 2 different libraries to do it. Both of these work only on a single computer. So if you're on your laptop, this is a great way to get order, factors of 4 improvement in speed. If you're working on a single compute node, that's also perfect. they do not work across compute nodes. So if I run into, I was like, oh, I want to split this across 10 compute nodes on Grace, this isn't going to be the right way to do it. And we have other tools that we'll talk about later. But you can do things serially with like a for loop, or you can do it with multiprocessing with a pool of workers. And in fact, we're going to talk about this. So this is the dangerous part of doing live coding. So we're going to see how it goes. So these are Jupyter notebooks that are available in the Git repository, so you can play with them in the end. But I wanted to, why are you not scrolling? Serial execution. So before we can talk about parallel, we have to talk about what's not parallel. So in this particular example, I've defined a NumPy array with 6 elements long. And I've defined a simple function that just returns the square of a value given. And then I can loop through that. And for every element in this list, I can print the return value of this function. So this is, just as you would expect, very simple. This concept of performing an action on every element in an iterable or a list or an array is the same concept as what's called a map. So I don't know if you're familiar with either an apply or a map. These are terms that are used in code to talk about taking a function and doing it on every element of some list or assembly of values. So I can very inefficiently write a map function that creates a container for the results. It then loops through the elements of whatever array I give it. And then I append the return value of whatever function I'm passing in. And then to this list, and then I return it. And so if I run this, I get an integer 64 of each of these, since I'm working with NumPy. But it's a container of these objects, where I've squared every element. Python already has a map function built in, so this does it just fine. We don't have to reinvent the wheel in general. Bad idea. But multiprocessing and several other packages have the ability to do a parallel map. So no step of what we just did. We squared an element in an array. None of those need to know about any of the other elements in that array. There's no interdependency in the actions that are happening. I'm not doing a running average. I'm not calculating differences. I'm just saying, give an element, square it. And that means that you can run it in parallel, right? There's nothing interdependent. You can do this. So in this particular example, we're going to start a multiprocessing pool. This compute job that I'm working in has 4 CPUs allocated to it. And I'm going to map this function on this list, just as I've been doing. But I'm going to use the version that's connected to this pool of workers. And a pool of workers really is just, I create, in this case, 4 different processes that are all waiting for instructions to do something. And they do them whenever I tell them, whenever I give stuff to these workers, they're going to do it in parallel. And so in this particular case, context has already been set. OK, fine. So it runs it in parallel, and it returns the same object as before. That's not really helpful. I can't see what's happening. And so it's useful to... So we have this test. The test says, don't just print out the value, but also print the ID number of the process that produced this value. This is just a simple test to demonstrate that these things are really happening by independent objects. And so if I do this on the standard map, every process is the same ID because they're all the same. They're just doing it one right after the other. With multiprocessing, if I run this, they all get different PID numbers because Python in the background has opened up different processes, and it's executing each of these functions on independent threads. One thing that you may also notice is these are not in order because they finish as they finish. And in this particular case, because they're so fast, they just kind of come and go whenever. But there's no guarantee that the the objects you receive are in the same order. So you have to be a little careful. That was a really dumb example. Let's do something that's somewhat more interesting. So a really common workflow, and this is common, my background's in particle physics, and running Monte Carlo simulations was a big part of the computing that I did as a scientist. So for those not familiar, Monte Carlo really does come from the name of a casino in where you're gambling. And so to some degree, you're kind of doing gambling with statistics. The idea is you're going to use random numbers to generate meaningful information. And in this particular case, we're going to generate a bunch of random numbers, and we're going to apply a test to those numbers, and we're going to then count how many pass our test and how many don't. And at the end, we're going to be able to calculate, to a pretty good precision, pi. So we all remember from, or at least I should, remember from basic geometry, the area of a circle can be calculated, the numbers, oh my God, my brain is not working. Let me take a step back. By generating numbers from 0 to 1, and then checking to see if the radius, or the square of the product of these two numbers, square of the, is less than 1, we can determine how many of them fall inside a unit circle. Because we're uniformly generating random numbers, the ratio of those two tells us how many are actually, will tell us the area of this circle, and from that we can get out pi. So this is just a simple visualization. We're going to generate two random numbers, x and y. We're going to then calculate their radius. If the radius is less than 1, it's in the circle. If it's greater than 1, it's outside of the circle. And we can then multiply by 4, since this is just a quadrant, and we get out the area of a circle. Okay, so this is a Monte Carlo method to calculate pi. This particular case, we're going to run 500,000 trials. We're going to generate 500,000 pairs of random numbers. We've got a counter. We're setting a random seed so that each time we run this with a different seed, you get a different list of random numbers. Random numbers on a computer are not actually random. We use that term, it's false. They're pseudo-random. You provide a seed, and it gives you a string of random numbers that is exactly reproducible, which is useful in certain contexts. But if you accidentally, say, use the same random seed for 100 of these different simulations, you get the exact same list of random numbers. There's no statistical difference between them, and you've done nothing productive. So you have to set the random seed to something useful, something that's different. And then we loop through these. So we take the number of trials, we generate a random sample, in this case from 0 to 1. We calculate the radius, and then we return the counter. And 4 times the counter divided by the number of total trials gives us pi. Okay, so we can run this. If we run it for random seed of 1, it took us 370 milliseconds to run 500,000 samples. And we can define a list of seeds. So let's say we want to loop through random seeds 0, 1, 2, and 3. And we do that, and we run it in series. And not surprisingly, it takes roughly 4 times as long. Is it finished yet? No, it's still going. So it's going to take roughly 4 times as long to produce 4 times as much data. That's not super useful. It took us 1.5 seconds instead of 370 milliseconds. I don't want to wait that long, and these are totally independent. There's nothing about them that needs to be run one after the other. So I can run them in parallel with a pool of processes. So I'm going to start 4 processes, and then I'm going to apply this function on my list of random seeds. If I run this, it's going to take not quite back to what it takes to run one of these, because there is a little bit of overhead in creating the pool of workers and assigning the work to them. But I get much closer to the single iteration, but I got 4 times the statistics. I did, square root of n better of the simulation with kind of 1 extra line of code. So this is a really, really nice way for smallish things to get higher throughput and better performance. Now, multiprocessing has a lot of tooling for it. the pool object is only one piece of it. It actually has a dozen different ways of working with things in parallel. It does stuff with threads and does stuff with, so it's a complicated library, but it has some problems. And actually the error that it threw the time that I ran it first is actually related to one of them. Multiprocessing is not always the best at working on systems like Windows. So the difference between spawning and forking of processes is somewhat lost in Windows land, and multiprocessing sometimes gets cranky. And so there have been some modern attempts to do this using, this particular one is called joblib. And it tries to make it a little bit more modern, a little bit more robust, and a little bit easier to work with. And in this particular case, joblib has a constructor called parallel. You can pass in it, how many do I want to run in parallel? What is the function? In this case, it's saying it's a delayed function, which is a little bit complicated to explain. And then you're saying, this is I for I in range of 10. So I'm giving it this iterator, and I'm applying it to this function. And you run that, and you get these, you get your array back of the 10 objects that it calculated. In this case, it calculated pi 10 times, and it did it in parallel. Now, what's nice is this number and this number don't have to line up. So in this case, I had 10 things I wanted it to do, and I said, you have 4 workers to do stuff on, 4 jobs. And so it did 4, and then it did another 4, and then it did 2. So the very end of it, it said, well, I've only got 2 left. I'll just give it to 2 of those. So that last part was inefficient because 2 of those CPUs were idle. That's not really that big of a deal. So it very simply can do parallel for loops. So yeah. Tyler.
Does joblib maintain the order of inputs?
It does, which is interesting. But I believe the way that it constructs the output, it kind of waits for things to kind of come back. So it might mean that you don't get results kind of in real time, but it does maintain the order. So another example, another thing that's really common is I have 10 different data files, or 1,000 data files, or 10,000 data files. I have to do the same processing to all of them. So this was common in my field, where I had a bunch of, I had an instrument that was collecting data. Every hour, it wrote out a data file, and it just ran for years at a time. And I ended up with thousands of data files that are totally independent. They all need to be processed with the same functions, but they can be processed whenever. Or I have 1,000 images from a microscope, and they all have to have the same pre-processing done. None of them depend on the others, so I can do them in parallel. And in this particular example, I'm just working, I've got a bunch of images of train stations because I like train stations. And in this particular case, I want to flip every image. So let's say I know that my instrument was upside down, or the images it collects are inverted, and I want to process all of them to put them right side up. So I can define a function that takes a file name. It extracts the base name of that, so it strips off the extension. It opens the file, it rotates it, and then it saves it as a new file format. So in this case, it takes it from a JPEG to a PDF. And then it returns the name that it saved it to. And so I have this list of data files, and I can use joblib to map this function on this file list with a certain number of jobs, and it returns all of these functions. This is the return value that says, here's the new names of all these files. And if I go and I actually look, I can pull up, this is, here's London Bridge, and then here's London Bridge flipped. So it's a different format, so it's a different image viewer, but you can see the text is upside down. Now, this is a really dumb example, or a simple example, but you could imagine this function being rather extensive. It could apply a fast Fourier transform. It could convert to grayscale. It could do lots of different things, or it could be a totally different data type. But the notion of, I have a function that's doing all of the processing of a single file. It takes an input, and then I can throw different input file names at that function, and it will work on them in parallel. That's an incredibly common style of parallelism, and it's often, I think, somewhat derogatorily referred to as embarrassingly parallel. I really don't like that term because most of the work that I did was embarrassingly parallel, and I didn't find any of my work to be embarrassing. But instead, I like to think about it as high throughput. The goal is I've got 10 million data files, and I don't want to wait 2 years for them to process. I want them to be done tomorrow. How do I process as many of them as fast as possible? So let's go back to the slides and talk about how do we take this and expand it. Yes?
How do you define like the number of jobs, like for example, of this function, how you define it?
Yeah, it's an excellent question. So in general, you have to match it. So you got a couple of pieces. You have how many CPUs are either on your laptop. You might have 6, you might have 10. If you bought a really beefy one, maybe you have 15. You don't want to go higher than that because you want there to be exactly a CPU for every one of your workers, that they have their own CPU so that they're not conflicting and fighting for resources. On the cluster, compute nodes can get rather large, right? We have compute nodes that have 64 cores. So you could, in principle, say, I want a 64-core compute node, and I'm going to give 64 workers, and I'm going to churn through. In practice, that job might take a long time to start because you're asking for a lot of resources to be available all at the same time. And someone else might be running on that compute node, and you might have to sit and wait for that node to become available. And so the resource request in that mode, you're kind of, how long do I have to wait for the job to start versus how long will it then take my job to run? You're kind of tuning these two back and forth. And that actually is a really good segue to this next pivot, which is on a cluster, and on our clusters in particular, that's an inefficient way to solve some of these problems that truly are embarrassingly parallel or high throughput style problems, because I don't need 64 cores all at once. I don't need them to be on the same compute node. I have a shared file system where all of the data are accessible to every compute node. And I shouldn't be doing the implementation of this parallelism myself, the way that I have to on a laptop. On a laptop, you don't have any choice, right? I don't have a scheduler on my laptop. I don't have anything that's working to help me there. I have to manage it. But on the cluster, we have infrastructure, and the infrastructure is really good at running lots of jobs in parallel. And okay, with multiprocessing, I could get maybe order 10. 64 might be approaching order 100 if you round up. But our compute nodes, Grace has 30,000 CPUs on it. We could run order 10,000 jobs at once on Grace using the cluster infrastructure. And so when shifting from working on a local laptop to working on the cluster, one of the big things that you need to take a step back on is, how do I leverage the cluster infrastructure rather than reinventing my own infrastructure to run things in parallel? And so the 3 steps that I try to work on is identify the kind of smallest independent component of your job. So if there's a thing that I have to do 1,000 of, I have to process 1,000 data files, or I have to do a whole lot of simulation, break it down into what can be run in parallel, and accept the fact that sometimes that might mean you have to do one step multiple times. So maybe it feels inefficient because I have to read the data in every single one of these jobs, and that means I'm reading it in 1,000 times, and maybe that's inefficient. But you can run them by running so many in parallel, and running them asynchronously in parallel. We can run 1,000 jobs, not just 100 or not just 10. So the cluster provides several ways to do this, and we're going to focus on what are called job arrays to do this in an asynchronous way. So I need a drink of water. So just to make sure, yeah, what's up?
Is there ever a point in using one of the, not the cluster arrays, but is there any point in using multiprocessing or job lib? I'm not sure what the overhead is to start a job and release a job. Is there ever a situation where the function you're attempting to parallelize is so simple that it's not worth creating and releasing jobs? Okay.
There are certainly problems that work that way, where there's a lot of pre-processing that needs to happen, and you can't really do that beforehand. There are certainly workflows that benefit from that. Or if the next step is really involved and needs the results from all of them to do an average, and then one thing that's really common, right, if you work with microscope data, is you might have frames, stills from a microscope, and you want to take the average of every single frame to remove some object in the background, right? That's an example of something that you need all of the information in memory to be able to do that, or you have to loop through. And for that, multiprocessing to spin it out, do a big parallel crunch to get that value, return it, then subtract it from every image. That might be a reasonable way to do that. Yeah. So there are you could also shoehorn it and do it in this way, but the point is to be science focused, and so whatever gets you to the science fastest, that's the right solution. So Slurm, all of our clusters run Slurm. Just to make sure, does anyone not work on the clusters or has not done any work on our systems before? Oh, thank goodness. Okay, so I can talk about this and not feel like I have to explain what a cluster is. Slurm is our scheduler. There are others. This one is ours. And it has a concept of a collection of jobs that are all similar. So they all require the same resources. And so Slurm can treat them like an array. And it says, this array of jobs, each job has an index that you can reference. And crucially, they all run independently, and they can all run asynchronously. So as resources become available, Slurm will start working through this array of jobs, and it'll start 2 jobs, and then another 2, and then 10 jobs, and then 100, because some big chunk of resources became available. And this allows you to leverage the cluster's infrastructure for orchestrating parallel jobs and not have to do it yourself with multiprocessing. You can construct these yourself in a batch script. And we also have written a utility function called DSQ that you can load as a module that kind of simplifies the creation of job arrays. We're going to work through both of these. But use cases are all of those things that we were just talking about with high throughput or embarrassingly parallel. Pipeline processing of a bunch of data files, or Monte Carlo simulation with definable random seeds, or maybe even a grid search. I have some big complicated space with a really expensive function, and I can say, discretize this space. Each job element, or each job array element gets a single point in this large space, and then returns the values, and I can then aggregate them and look for some minimum or maximum. It's not maybe the most efficient, but it's surprisingly common. So let's do an example with that Monte Carlo pi definition. In this case, we're doing it a little bit more NumPy friendly. We're not doing any for loops. But so here, we're going to, we have the ability to pass in the number of samples and the random seed. We set the random seed so that all of our jobs have a unique distribution of random numbers. We generate a bunch of x's and a bunch of y's. We calculate the radius of those. We get the number that are less than a radius, and then we return pi. So this is the same thing, but just slightly different code. And then, very importantly, we want to pass information in on the command line. So what do I mean by that? So that when I run Python function name, I can give it an input. So there are lots of ways in Python to manage inputs. This one is using kind of the lowest level, simplest one, which is called argv. It just gives you a list of things that follow the function name or the file name. But in this case, I'm just saying, look, there's going to be one of them, and it's going to be the random seed number. So whatever number I'm passing here on this is the number that defines the randomness. And then it's going to print out the element array. So this is annoyingly hard to see. So every job array gets a unique index, right? And it does so with an environment variable. So Linux uses environment variables as a way to store information that's accessible across lots of different processes. And the one that I want to use right now is the task ID number, with that index. And so this is that name. This is slurm array task ID. This is set, for this particular example, either 0 or 1 or 2 or 3 or 4, all the way up to 10. And so I'm going to run 11 versions of this job with different inputs. And then I'm going to print out the result from each of them. So if I submit this batch job, it's going to run 11 copies, each with 1 CPU, each with 10 gigabytes of memory. And it's going to print out in 10 or in 11 different data files. These are the results from each of these. So this is the index number. And since Linux sorts kind of in a funny way, you get 0, 10, 1. But these are the values of pi calculated by each of those functions. And then, so you get independent results. They happen asynchronously whenever that job happens to run. If one of these elements finishes and there are more jobs that are pending, it'll just pick up the next one. It'll assign it just like it normally should. And then you can take these values and you can average them, or you can combine them in some meaningful way. In this case, since they're all different Monte Carlos, you would average them to get an even better version of pi. But if it's data files, maybe you have the next step in your pipeline that you aggregate, calculate some moments or whatever. And you can do that with a cleanup script. So you write some function that pulls the outputs from this earlier process and aggregates them in some way. So this is not terribly complicated, but you could imagine there being a lot of steps that maybe are more complicated, especially if you have a function that has not just one input, but maybe a dozen inputs. It's some really complicated space that you're doing that grid search through. And so maybe you don't want to do that in a native batch script. I'll just say these are the different array environment variables. You get the ID of the parent job, but then you get the specific index. You can also get the min and the max and how many there are. That can be useful for a variety of things if you want to, but use these in your batch script. And this is the main one that's really meaningful. This is a good one for doing multiprocessing style parallelism. You can get the number of CPUs that have been allocated to your job. I just wanted to throw that in there. It's a little bit out of order. Okay, so if you yes?
What is the maximum number I can submit?
Yeah, so the maximum number on Grace is 50,000. They won't all run at once because we only have 30,000 CPUs and there are limits, but you can submit 50,000 and it will just happily churn through them. You can also say, here's 50,000, but only run 1,000 at a time. And so you can put a limit on there just so that your group mates don't get mad at you for taking all of the resources. That's a good question. I think on McCleary that number might be 10,000, but it's a definable number on our end. And if there's a compelling use case for why it should be higher, let us know. Yeah.
So Slurm can do things by CPU versus node?
Yeah.
So it'll farm it on whatever it is.
Absolutely. So that's really where you win, because the number of times this job does not need a lot of memory, and it's really common for there to be free CPUs on a random compute node, but not a ton of memory. But there might be one here, and maybe 2 there, and 3 over there. And Slurm can say, oh, I can put a job there, I can put a job there, I can put 2 jobs over here. And so you don't need to wait for a whole node to become empty. Slurm can just fill all the cracks. So that's a reason to appropriately set the memory request. So if you have a job that doesn't need a lot of memory, don't ask for a lot of memory. Ask for a sensible amount, and Slurm can find these resources that might otherwise go unused. That's a good question. Okay. Sometimes you have something that's more complicated. Maybe you want to pass a data file name, or you want to do something that's not simply just give an index that starts at 0. And so DSQ is a way to take a text file that contains new line separated list of commands, and then to, so in this case, here's my text file. I'm going to have that same function that I defined before, and I'm going to give it an input file name of the JPEGs of these images that I want to process. And so each line of this text file gets its own independent set of commands. And then if I pass this job file to DSQ with the resources that are required for it, it then generates a batch script for me. This batch script is not exactly the most user-friendly, and annoyingly, this is not as clear and easy to read, but it builds the whole structure. And all you have to do is run sbatch of this file name, and it will submit the job array. And each element of the job array will process one line of this file. You can separate commands with semicolons. So if I have a pipeline that has multiple steps, you can separate those steps with semicolons. And they'll just happily run in parallel. And this file, right, can be 50,000 lines long. I don't want to type 50,000 lines into a text file, but I could write a script that does that pretty easily. And so you take, you have a little for loop that just generates the output. You save it in a text file. You submit it to the cluster with DSQ, and now you've got. I wrote a simple for loop, but the cluster is running them all in parallel. DSQ also has a really nice feature that's called an autopsy. It's a little bit morbid, but the idea is that jobs fail, right? It's not uncommon for a job to fail. And if I submitted a job that had 50,000 elements in it, I don't want to rerun 50,000 just because 7 of them failed. And so DSQA can give a report of how many of my jobs are running, how many have failed, how many have completed. And if you actually pass it the job file, so if you give a -f with the file name, it will print out the subset of those lines that need to be rerun. And you can just copy and paste that into a text file. And so now, instead of saying, okay, well, I had 50,000, 7 of them needed more memory than I allocated, here are the 7 in one text file, and I can run that with slightly more memory. So it's a really nice way to clean up. Yeah?
So if I'm submitting a job array, I should estimate what's the, which job will require, what's the maximum, RAM required by one of the, job, and then pick the biggest one to be safe. Right?
That's generally the right approach. Sometimes you get that number wrong. Excuse me. But that's the right approach. There is a similar issue might come. You pick a time, a run time. You say, okay, this should take 6 hours or should take 1 hour. But a handful of jobs take 20 minutes longer. They all get killed. I don't want to rerun all of them. If I run the autopsy, I get just the list of ones that failed due to timeout, and I can extend their time when I resubmit just those jobs. So it's a convenient way to keep track. Yeah. For each.
For each job.
That's what's really wonderful. So this hour that I'm specifying here, all of these resources, 1 CPU, 2 gigs of memory, and 1 hour, that's per element. And the time is based on when that element started. So, let's say I have 1,000 data files and I want to run serially or with multiprocessing even. It might take longer than a day. It might take longer than a week if I want to do that on a single compute node. And you start to run out of time. But here, the time limit is per job element. And so you can run 1,000 of them, and it's an aggregate of 1,000 CPU hours, but the limit only ever applies to one element at a time. Yes?
Are there any difference if I want to run an array on GPU partition?
No, it's the same.
Okay.
The limits, so the 50,000 is the number that you can submit. The number that runs is the normal QoS limits, the normal limits in whatever partition you're working in. So if you are running in GPU, you're going to be limited by the number of GPUs that you're allowed to have concurrently, which is on Grace, I think 20, something like that. But yeah. Okay. So cluster-based parallelism, it pays to think wide. It pays to think, how can I run this on multiple compute nodes leveraging the built-in infrastructure of the cluster rather than how can I get it to run on a single compute node and manage the infrastructure myself. And I'll just a note, linear scaling, if I give twice the resources, does it run twice as fast, is really hard to achieve. But it's really easy to run 2 jobs at once. And so, and that's linear scaling. And so it may be the case that if I want my job to run fast, I don't want to tune for a single element of my job array. I want to tune what's the fastest way to process all of it. And that may be running more of them in parallel with each of them being a little bit slower. And so if you have 10,000 of them, you have to think about the whole job, the whole picture, rather than how do I make one element run a little bit faster. Okay, this last section is about how do we okay, we've talked about best practices, we've talked about cluster, we've talked about resource monitoring. What if that's all still too slow? How do I make that next step in complexity to get more performance? So we're going to focus on 3 libraries that do things in kind of 3 distinctly different ways. There are a million of these, but these are 3 that I think are worth highlighting. The first is numba. Numba is a way to compile Python code into it's not really into an executable, but into something that the compute node can execute more natively. Dask is a tool that takes NumPy and pandas and expands it into something that can be run across multiple compute nodes, and also can deal with larger than memory data file size. And then cupy is a tool that takes the NumPy language, or the NumPy API, and converts it to something under the hood that can run on a GPU. It started with CUDA, which is why it starts with a prefix of CUDA, but it also has now recently started working with AMD GPUs. So if you have something in your local machine that isn't produced by NVIDIA, this also works. Okay, so numba, what is a compiler? It's a really big question. I'm going to answer it in a single line and then completely gloss over it. A tool that takes human-readable code and converts it into something that a machine knows what to do with, into machine-readable instructions. Broadly speaking, that's a compiler. That's as deep as I'm going to get into it. Numba is a flavor of a compiler. It's called a just-in-time compiler. So if you've ever worked with C or Fortran or anything like this, you write your code, and then you say G-Fortran this thing with some libraries, and it produces a binary executable. You do it all up front. Numba isn't like that. When I call my Python code, Numba is watching, is, oh shit, he's going to get to a function that I've been told to compile. And so just in that moment, the first time it hits it, it's going to compile it into machine-readable code. And then it's going to just cache it in a little hidden directory. So the next time that my Python code hits that function, it's going to pull the already compiled version. So it's going to start, the first time it hits it, it has to actually compile. That may take a little bit. But the second and third and fifth and millionth time that I run that function, it's leveraging the already compiled version. The nice thing about numba versus there are other ways to do this, there's one called Cython or Cythonize, and there's a bunch of other, but the nice thing about numba is that it's really minimal modifications to code. So you just sprinkle in what are called decorators. These are little annotations that you put in front of a function to say this function, yeah, compile that, and don't worry about the rest of it. And there are order 10 to order 100 speedups that can be attained depending on the scale of the problem. It can be extended to CUDA, and you can compile Python code in a way that can run on a GPU through numba. I'm not going to talk about that today, other than to say it exists. So, okay, here's our NumPy Monte Carlo, the calculating pi. We set a random seed, we generate the samples, we raise it to the second power, and we apply the filter. Same as we did before. Here's the same kind of thing written in numba, or written for numba. We add this line here that says just in time, so you put a little ampersand that says, or the little @ symbol, JIT, so just in time. This is saying don't use any Python, compile it all into machine readable. And this is saying, if possible, run sections of it in parallel. And so then I just give it the same number of samples. I set a counter. Instead of using a normal range, I'm using a p range, a parallel range. This is another numba function. So for I in p range of n samples, do this thing, and then return pi. And if you do this, so this is a comparison in the runtime in seconds versus the number of samples that you're calculating. And there's a basic one that just is lists and appends and has nothing fancy in it. And that runs in kind of order n time and takes up to about 40 seconds to run 10 to the 8 samples. But NumPy and numba, but if you start parallelizing numba, all of a sudden you're getting not just a factor of 10 or a factor of 20 improvement, but maybe a factor of 200 improvement over the very simple nothing fancy function. And this is not a complicated thing to write. It's just saying, hey, this for loop can be parallelized. Why don't you parallelize it? And then just in time compile it. The thing that's interesting is for small number of samples, numba takes longer than standard Python. And that's because it has to compile that function, right? Nothing's totally for free. It takes time to compile that function and to import the extra libraries and do all of these things. And this is why scale matters. If all I care about is 10 to the 3 samples, in this particular example, I should take NumPy, pure NumPy. But if I care about 10 to the 8 samples, I'd be a fool not to use numba. It's 20 times faster than NumPy. So scale matters. And in that flow chart that we talked about at the very beginning, quick and dirty, is it fast enough? Does it work at scale? So scale is important. There are also codes that are not really vectorizable, right? I mean, this code here, all of these lines are working on a vector or a full array. You know, NumPy takes these two arrays as inputs. It acts on them in concert all at once. But there are algorithms that you can't really do that with. And a really common one is calculating the behavior of particles in a box with some Lennard-Jones type potential, something that depends on the location of other particles. So it's not independent. All of these particles are dependent on each other. What they do depends on their nearest neighbors. And I don't know how to vectorize that. Maybe someone really clever could vectorize it, but I'm not that clever. But I could write a numba function, compile it in numba, and this comes from the examples from the numba website. And here's kind of standard NumPy. And here's what happens if you start using numba in parallel. You get 60 times faster performance when you're at scale. Down here maybe it's not so big, but a factor of 60 improvement is quite impressive. So there are algorithms that lend themselves better to vector operations. There are algorithms that don't. And so understanding your particular problem and your particular use case can guide you. And numba is a tool that can really help accelerate non-vectorizable codes. Okay, simple Python can be compiled to very efficient code. It's especially useful for non-vectorizable operations. I will note, numba really likes to have data types. Python is like, it's always loose with what data type. I'm going to say this is a list, but later maybe I'm going to throw some random object into that list. And Python has to work really hard with memory allocation to make that possible. Numba really benefits from you saying, this is a float of this size, so that when it compiles it, it doesn't have to worry about all those edge cases. It says, I know exactly what this is, and I can treat that very efficiently. So that's an important thing to keep in mind, especially for people who are new to that style of programming. For small jobs, overhead of compiling can actually be a net loss. You can spend a lot of time compiling functions that maybe you don't need to do frequently, or maybe you don't, maybe it doesn't help you at scale. But for frequently executed sections of code, it really can have a dramatic improvement. Okay, yeah?
Yeah, so can you use other Python packages within Numba? For example, if I want to use a fitting function within SciPy and I want to parallelize, so there's a simultaneous fit over.
The answer is probably. Not every function plays nicely. but a lot of NumPy and a good chunk of SciPy do. That's a really good question. It's not a uniform tool. Any other questions on Numba? Okay, Dask. So it's really common to have data that you want to do whole operations on, but I can't fit it in memory. Grace has a couple of compute nodes that have 4 terabytes of RAM, which are kind of insanely expensive to buy. They're really useful, but sometimes I don't want to wait for my job to run because someone else is on that node, and then we only have one of them or 2 of them. Dask takes a high-level approach to splitting up jobs into independent, discrete tasks and spawning them over multiple workers. Those workers can be local, or they can be distributed. So on your laptop, you might use this as a way to chunk and work through data in parallel instead of multiprocessing. But on the cluster, you can say, dear Dask, start up 100 workers that are scattered across the cluster, do operations on these different data files, and return the values to the head worker, and then collect the results. So just like NumPy, there's a concept of an array in Dask, and you kind of get parallel execution for free or out of the box. Same with tabular data in Python or with pandas, but you have Dask data frames that have a very, very similar API. They act and behave just like a pandas data frame, but they are executing in the background. Now, Dask leverages something that's called lazy execution of code, which means it doesn't actually do anything until you ask for the result. And it does this so that it can orchestrate the whole package and say, this I can run here, this I can run here, I need these results together. And so it builds what's called a task graph. So you have collections, which are these objects that contain different, they either contain, in this case, a vector of data or tabular data, or a bag is more like a struct if you've worked in other languages where it's a collection of different data types. A delayed is a function that it might wait on the result for. Futures are the flip side of that, where you're expecting a result from something else. And it builds this task graph that says, this is the work that I will want to do when you say go. So you run all of the commands to build this up, and then at the very end you hit compute. And it processes it either on a single machine or distributed across multiple computers on a cluster. So we're going to actually do it. Again, the dangers and fun of live code. So let's go to the top. So what does this look like in practice? So here we have, this is a Dask array. It's 1 million elements. I've generated random numbers. And I've just reshaped it into being 2,000 by 500. So it's a big, the whole thing is maybe 7 megabytes. This is not a large one yet. And so Dask gives you this nice view of how it's thinking about the data. And I've told it that it can chunk things into blocks of numbers that are 100 or 100 by 100. So each of these has 10,000 elements in it. And I can then strip out parts of it. And I can say, OK, give me up to 500 in one dimension and 100 elements in it in the other dimension. And I can start working on slicing and dicing the same way that you can with pandas. But I haven't done anything until I actually hit compute. That is when it goes and actually produces the value. In this case, I'm just generating some random numbers and I'm building it from an array. But I can do operations, like I can calculate the average value, or I could calculate the standard deviation of these numbers. But it doesn't do it until I hit compute. That's not sufficient. I have to, and this is useful because sometimes you want this to be like the product of 10 or 15 lines of code, a bunch of different operations that all culminate in one line, and I want to do it all at once. The fun happens here. So Dask knows how to talk to Slurm. And so during the break, Jorge was asking about, can I launch a Slurm job from within Python? And the answer is yes, in several ways. This is, I think, the most useful. I'm going to create a cluster. We're going to use that term. It's an overloaded term, but we're going to use it here because that's how Dask refers to these. And this is the information that I'm telling Slurm about my workers. So each worker needs 1 CPU and 20 gigabytes of memory. And I'm going to submit it, in this case, to the admin test. That's a partition that's on the cluster. It's just so that we don't have to wait. But this could be day, or this could be GPU, or this could be whatever you like. In this case, I'm going to scale it up to have 10 workers, so 10 copies of this. And then I'm going to connect to it. And so I now have a cluster of compute resources that I can, in particular, pull up this beautiful little dashboard. So Dask has a way for you to monitor what your work is doing. And I'm going to move this to a new window so that we can have these things side by side. Let's do this. Let's do this. And so now, let's start doing something with not megabytes, but gigabytes of data. So we're creating this, and in this case, we can see, well, let's make this bigger. So we now have data stored on every worker, and we can compute the standard deviation of these 2 million values. And of course, so here we go. So we're processing several tasks, and in a moment, it's going to start doing real work. So each of these rows in this visualizer is one of the workers. These are the way that it's chunking the operations to run asynchronously in parallel. And then it's returning the value back to the main thread. Now this was a really dumb example. Let's do a fun one. So is anyone familiar with the New York taxi cab data? Okay, so New York City collects for every ride in a yellow cab or an airport cab, or now Lyfts and Ubers, ride shares, information about every trip that's run across the city. As you can imagine, this is an obscenely large data set. You can just download these data. It's a wild amount of information. It includes where is the trip from? Where did it go to? What was the distance? What's the mileage? What was the tip? All of these things are stored and are provided to the public, which is crazy. And so we're going to use Dask to ask some questions of these data. So let's make this big again so we can see. Come on. Okay, I can't do that. So I'm going to load in the yellow cab data and the rideshare data, the Uber and Lyft data. And so I have the data from, I think, 2023? 2022. So this is a whole year of these data. Every single taxi cab ride for a whole year. And I'm going to read them in. Now, nothing's happened yet because it's building the task graph. Then I'm going to filter and say, give me the trips where the fare is greater than 0. So it actually happened. It didn't get canceled. And then I'm going to ask the question, do people tip better for yellow cab or for Lyft and Ubers? Which is easier? Which yields greater tips? And I'm going to actually plot it. And so here it's starting, oh shit, got to hide the results. So it's actually going through, it's loading the data in these different workers. So it's reading them across the cluster. It's then processing them independently, collecting the results, and it's sending them back. And you can see, okay, now it's storing a certain amount of memory on each. So 8, 10 gigabytes per worker, and then it's performing some actions, and then it's going to return the values, and it's slowly crunching through the different tasks that it has in its queue. And in a moment, we'll have the result. And in a moment, we'll have the result.
Is there any overhead like having this?
Absolutely, yeah. No.
What's
so this is running, the launcher is running in a compute node,
Right.
but all of the work is happening on the workers.
Got it.
So all of the data is being read in by the workers, which is really useful for working with data like this, because you don't want to read all the data into the head node and then throw it out. You want to tell each of the workers, load this yourself, and then they get the benefit of the parallel file system, and you're not relying on network. So I forget that because I'm doing both the yellow cab and the rideshare, has to do them sequentially. So here we go. So now we can look at the data, and we can see the distribution looks really different, right? The yellow cab has a peak at around 20%. Now, I think it's fascinating that this goes out to 200%. This is in, it says percent, but it is in fraction. So it's not 0.25, it's 25%. So these are big tips. But if we look, yellow cab averages 22%, Lyft and Uber average 4%. That's fascinating to me, and I don't really know what to make of it. It seems really wild that there's such a difference, and maybe there's something different in the way that they're collecting this information. Maybe the data have something different in them. But I just processed a year's worth of yellow cab data and a year's worth of Uber Lyft data, millions and millions of entries, and I did it in a couple of seconds while talking to you guys. That's kind of fun. And at no point did I run into memory problems on my computer, even though these files are massive. Okay, so Dask, it's a fun thing. The challenge, or a challenge, if you want this fun display, this runs on a random port. So you have to run this all inside of a Jupyter, or inside of a remote desktop session on the cluster. You can't do this in our on-demand Jupyter app, because it doesn't do the port forwarding properly. Yeah, such is life. Okay, questions on Dask? Yeah?
You have to do the Slurm configuration yourself, or have you guys done it? Like, probably it's different for every cluster.
So it's, all you have to do is that one line. That one line that I did, that's it.
There's no configuration file?
There's no ini file, there's no configuration. So you have to install there's a package called JobQ, Dask-JobQ, and it basically is all the hooks to say, this is Slurm, this is how you talk to Slurm, but it's writing batch scripts. It's kind of, actually because I didn't run the close, which I should do, I can also show you what it looks like. So in SQ, can everyone read this? Maybe not. How do I make this bigger? I don't know. View, zoom in. Each of these is an independent job, Dask worker, Dask worker, Dask worker. And they're all running, looks like most of them are running on one compute node, but some are running on a different compute node. They've all been given 20-ish gigs of memory, one CPU, and a time limit that's defaulting to 30 minutes. I could tell it to be longer or shorter as needed. But it's not until I release them, so I come back here, and I do cluster.close. Now, if I come here, all of those jobs have been canceled and have been closed out. But that was all happening in Dask. And that's kind of fun, right? You can, in a Jupyter notebook, you could say, this cell needs a lot of resources. I'm going to spawn it out to 100 compute nodes. And as soon as it's done, I'm going to shut them down. But for that 30 minutes, I ran on 100 different compute nodes, but all from the comfort of my Jupyter notebook session. You just have to remember to close them. Otherwise, they sit idle, and that's a waste of resources. So, OK. Dask. Nice and fun, high level, very Pythonic. Larger than memory data sets you can work with as if they were local. And Dask distributed and Dask joblib are really JobQ, not joblib. I'll fix that in post. OK. The last thing that we want to talk about today is cupy. Sometimes CPUs are not great. Sometimes CPUs are really slow. GPUs are great. GPUs are a lot of fun. How do I program a GPU in Python? The answer is I don't really want to. I want someone else to have programmed the GPU in Python, and then all I have to do is talk to that high-level library, because programming for GPUs is a complicated mess. Cupy takes the NumPy functionality, the NumPy functions, and just replaces them with ones that know how to talk CUDA. It often works as simple as, instead of import NumPy as NP, you can often just import cupy as NP, and it kind of just works. But it can handle multiple GPUs. You can have a lot of fun with it. So let's do, this is some promotional stuff from the cupy website. So again, scale matters. For 8 megabyte or 800 megabyte arrays, you get different performance improvements, but the speed up is potentially wild over standard NumPy. 200 times faster, 50 times faster. This is kind of fun. So let's do some cupy. All right, so we're going to import cupy as CP so that we can compare right next to each other. Now, in this particular one, I have requested a GPU. None of this works if you don't request a GPU. So, full disclosure. But so let's do some random number generation. We just have two big random numbers. They're big arrays. We're going to shape them into 5,000 by 5,000 matrices, and then we're going to multiply them. It's about as dumb as you get, but let's try it. So this is running it in NumPy, and it's going to print out how long it took in just a second, but that's giving you an indication of how long it takes. These are big, big numbers, and hopefully it doesn't run out of memory. Okay, so it took almost 4 seconds to do each loop. We're going to do the same thing, but we're first going to move them to the GPU. So we're generating them in NumPy same as before, and we're reshaping them in NumPy same as before. But we're adding in this statement where we take it from being in standard memory to being in the GPU memory. And we're going to, let's do this, make this a little bit bigger. We're going to run NVIDIA SMI. We're going to watch as it runs. So it starts doing everything in the CPU. Oh shit, it's finished already. We didn't even see it. See if we see a little, we see it here. Oh, spiked to 100% for a second, and then it goes away. So instead of taking 7 seconds, it takes half a second. Or sorry, instead of taking 3 seconds, it takes half a second. 7 times faster. And that includes moving the data. So we had to take the data from the CPU memory, from the standard RAM, and move it to the GPU. And that's often a bottleneck with GPU-based stuff. So even factoring that in, it ran 7 times faster. Okay. That was a simple toy. Let's do this with some of that yellow cab data. So in this case, let's look at data over time. We're going to look at the January data and the July data. We're going to read it with pandas, and we're going to then strip out the tips in January and the distance in January. So how long were trips in the month of January? How much tip did they get? We're going to do the same in July. We're going to schlep the data to the GPU. So now this should update to have more memory used in a second. Maybe it already did. And then we're going to see which is more efficient for the cab driver. So first, this is what it takes in NumPy. This is what it takes in cupy. So it took 6 milliseconds to divide these things in NumPy. It's going to take 170 microseconds, so quite a bit faster to do this division on the GPU. But let's see the tip efficiency. So dollars per mile of trip length. Do cabbies make more money in the summer or make more money in the winter? Is it like, oh, it's so hot outside, I'm going to be so thankful, I'm going to tip more? Or, oh God, it's snow everywhere, I'm going to tip more, thank goodness that I'm here. The answer is it's almost exactly the same, which is also kind of funny that there's a little bit higher tip on average in January. And interestingly, you can see the overall scale. This is not a normalized histogram. So there are more trips done in July than in January. And that kind of makes sense, right? there's tourism, people are coming to visit the city in the summer, so maybe there's more trips on average. But the distribution is pretty similar, and the average tip is pretty similar. So, and the act of doing this, we can't even really see it on the GPU, it's so fast. But we can do this sort of work without complicated CUDA code, without writing our own CUDA kernels, but we can use Python to get order 10 times speed up for simple stuff, and for complicated things, sometimes order 100 times speed up by running it on the GPU. So, to sum up, human time is expensive, compute time is relatively cheap. It's important that we keep in mind when trying to tune and optimize code, we shouldn't neglect the time it takes for us to write that code. That's part of the whole pipeline for science. So using a language like Python, which is friendly to write and friendly to work with, and easy to debug and easy to profile, can have really big dividends in terms of the total throughput of science. But it shouldn't mean that we have to sacrifice performance. We can get more performant Python code by profiling, by scale studying, and by tuning and optimizing and deploying these accelerators when we find that the standard tools are not sufficient. And when running on the cluster, always look for ability to break up jobs, run them independently, and recognize that we've worked with different data, the same types of data in wildly different ways throughout this tutorial, this workshop. And you can see the benefits of each of them. So there's a lot of ways to solve every puzzle, and keep trying new things. So with that, I'm going to throw up the better flow diagram and say thank you, guys. We have a few minutes for questions. I'd also be happy to stick around, and if people have specifics to their workflows, I can chat about it. But yeah, thank you guys so much for coming. Are there any questions? Or yeah.
For the cupy things, do I have to cut my data if it's too large?
Yeah. It doesn't chunk data nicely the way Dask does. I believe there is a way to use Dask with a CUDA backend so that Dask is doing the chunking and it's aware of how much memory is on the GPU. But I've never actually played with that. But yes, you have to be careful of GPU memory.
Thank you.
Yeah. Yes?
Do you have any pins on jacks, which some people are using?
Yeah, I had an intention of including jacks. It might have gone out in the announcement. And then I got deep into it and realized I couldn't wrap my brain all the way around it. JAX is a library that's written by the TensorFlow folks. And people use it for automatic parallelization and things like that. It got more complicated than I was able to prepare for this. That's not to say that it's not useful and valuable. I've seen people using it on the clusters. So I know that some people are finding value out of it. It just very quickly got out of scope. Awesome. All right. Thank you guys so much. Happy coding. See you later.